We'll expand e to the x as a power series in this form. The a's are coefficients labelled to match the power of x, so for example a3 is associated with x cubed. We'll assume we can expand e to the x like this, and if we find values for the a's that work, then we probably can, and if we don't, then we probably can't. Now we'll substitute in x equals 0. On the left-hand side, e to the 0 equals 1, because anything to the power of 0 equals 1. On the right-hand side, only the coefficient a0 survives. The other terms are all 0 because they contain a power of x, and x equals 0. This means that a0 equals 1. So far, so good. Now we'll differentiate. On the left-hand side, that's really easy because e to the x is the derivative of itself. On the right-hand side, we just differentiate each power term individually by multiplying by the power and reducing the power by 1. For a1x, the power of x is 1, so we multiply by 1, no big deal, and drop the power to 0. And we've already said that anything to the power 0 is 1, so the derivative of a1x is just a1. For a2x squared, we multiply by 2 and drop the power of x to 1, and x to the power of 1 is just x. For a3x cubed, multiply by 3 and reduce the power from 3 to 2, and the others work the same way. Now substitute in for x equals 0 again. The left-hand side works just the same as last time, e to the 0 is 1. On the right-hand side this time, only the a1 term survives, because it is the only one without a power of x to make the term 0. Then we repeat. Differentiate, following the same method as before, and there's a reason that we're keeping these multiplication coefficients separate, so 3 times 2 rather than 6. It will hopefully become clear in a while. And these dots are multiplied signs. And substitute in x equals 0. Again, as before, 2a2 survives and the rest are 0. Differentiate. And substitute x equals 0. The 3 times 2a3 is the only one to survive. Differentiate. And substitute. 4 times 3 times 2a4 survives. Can you see now why we kept the multiplying coefficients separate? It's because a pattern is emerging that would be harder to spot if we'd evaluated these numbers. If we carried on differentiating and substituting, we'd get these as our next expressions for a5 and a6. Now we've discovered the values of the coefficients, let's just move them over here so we can give them a bit more space to explore them in. It's actually easier to spot the pattern by working from the bottom up because the numbers in the green shape are all easily recognised as factorials. The number multiplying a6 on the right-hand side of this equation is 6 factorial, so a6 is 1 over 6 factorial. Likewise, working up, a5 is 1 over 5 factorial, a4 1 over 4 factorial, a3 is 1 over 3 factorial. It can take a little while to realise that a2, a1 and a0 are actually following the same pattern. a2 is a half, which is the same thing as 1 over 2 factorial because 2 factorial is 2. Likewise, a1 is 1 over 1, which is the same as 1 over 1 factorial because 1 factorial is 1. The hardest one to spot is that a0 equals 1 can be expressed as 1 over 0 factorial. It will take this video off track to explain this here, but it's true and we'll provide a reason after the video. This means then that all the coefficients can take the values 1 over n factorial, and this means that we can write e to the power x as a series expansion in this form. And this is the power series expansion of e to the x.